I think we'll just start right on time and make sure we can skip straight to the content, but I'll do a little bit of introduction. One of the things I've always appreciated about our programming languages community is the close ties between academia and industry. I mean, you can literally, see that on the slide, and so I was really honored when Evan asked me to chair this session on the industry session at PLDI, especially with speakers from Apple, from Amazon, two companies that have long supported PLDI, really long interest in programming languages and support for that work. So I'm going to start by introducing John McCall. John McCall's been at Apple for 2 decades.
About right.
Working on Objective-C, Clang, C++, and now he chairs the Swift language committee. So he'll be talking about that today. A fun fact about John is that he is an avid woodworker. And I think today's talk will demonstrate some of that appreciation for joinery, for how things fit together in this talk on balancing high and low level programming in Swift. John, please.
Thank you. Hi, my name is John McCall, and I'm going to talk today about how Swift balances high and low level programming, especially for core features like value ownership and lifetimes. Our goal with Swift was always to have a language that could be used throughout the stack. Swift has been widely successful with application and library development for a long time, and more recently we've had success adopting Swift in lower level environments, even in kernels and hypervisors. And today I want to talk about what we've done in the language design to make that possible. Low-level programming has fairly strict requirements, which mostly come down to programmers needing to have control over costs. For example, it's not that you can never do heap allocation in an environment like the kernel. It's that you should only do that allocation when the programmer asks for it. And they need to be able to handle conditions like allocation failure. In memory-safe languages, the language and library make a lot of policy decisions that can add costs like this. Giving the programmer control over that usually means adding complexity to the language and library. For example, a safe language for low-level programming almost certainly needs multiple array types to represent different policies for how that array is stored and owned. I've listed only some of Swift's array types here, more are necessary really. All else being the same, it'd be nice to not need all of this, but it's really essential for writing low-level code. But higher-level programs often have very different needs. Application programming especially is prone to having a lot of redundant glue code, especially if you have to write that code all out explicitly. The performance of that code, meanwhile, is often not very important, and incurring a small overhead to make that code easier to write and maintain is very likely to be a good engineering trade-off. From that perspective, the same essential complexity that supports lower-level programming often feels more like an unnecessary burden on the high-level programmer. What we believe is that there's a solution to this conflict that works well for everyone, and I'm going to sort of spell it out here. When you see a conflict like this, you try to find a core implementation model for your language that works well for low-level programming. That means that essential complexity I described is still always there under the surface, but you design the language so that it doesn't force every programmer to deal with it up front. You pick reasonable defaults, and you push people towards acceptable common solutions that work as a sort of basic baseline for how to write code. And you can use that as the core of how you teach the language to new programmers. That gives you a lot of room to build out a more advanced feature set for the under-the-covers stuff to support the lower-level programming that you need. In this talk, I'm going to explore that in the context of 3 different interesting feature areas of Swift: exclusivity, value ownership, and non-escapable values. We're going to start with exclusivity. The design of Swift centers around our concept of value types like structs. You can declare a simple struct type like this. Every value of this type is owned by a single context in the language and has independent storage for all of its properties. When I copy the value of a variable into a new variable, like this, I have to copy all of these properties. But in return, I get something that's completely separate from the old variable. Modifying the original variable has no impact on my copy or vice versa. In short, I don't get any of the problems of shared mutable state. Now, those problems are very well studied in PL circles, so I'm not going to belabor that in this context. But suffice it to say that allowing multiple references to mutable memory makes a lot of things harder or worse in the language. Now, the fact that value types don't behave like shared mutable state is really valuable to us. We want that to be true. And it actually is true automatically for a lot of basic patterns of code. But there are places where the language needs to be more explicitly restrictive. One of them comes up with closures. Suppose I have a higher order function like this. It takes a mutable reference to an array, and as the self parameter of the method, as well as a function value as an explicit argument. I can call that method like this, passing a closure as the function value. And in this simple example, I haven't broken anything about value types. There's nothing wrong here. I've just got a closure and a separate array value. But what if I capture a reference to the array in that closure? Now we've sneakily made a second reference to the variable while it's also being used as the self argument. And I could really do anything to that array in this closure, even mutate it. This turns out to have all of the same reasoning concepts for the language as shared mutable state. In the implementation of the remove method, we now have to worry about whether calling the closure that was passed in will change the array or any of its other parameters. And this is really bad for the semantics of the language. It's also really bad for performance. If it's legal to alias like this, maintaining memory safety means giving up on a lot of important optimizations. For example, when we're passing self at I to the closure here, we really don't want to have to copy the element out of the array just to pass it. But if the closure can mutate the array, it can invalidate this element, which would mean that just borrowing the element out of the array naively like this would potentially leave the function in a state that is no longer memory safe. So the only safe option if I have this aliasing would be to copy the array, to copy the element before I make this call. As a result, that doesn't really work with the kind of low-level performance that we want to be able to support for low-level programming or just in general. Instead, we have a rule that we call exclusivity, which says that mutations of a variable can never overlap with any other access to it. In this example, Swift prevents the capture of the variable from overlapping the mutation of it that happens when it's passed to the method. This all happens at compile time and has no runtime overhead. It's a simple data flow analysis, very similar to the borrow checking done by Rust. But Swift doesn't just have value types. We also have classes. The basic programming model of classes is similar to the model of classes in most traditional object-oriented languages. It's inherently based around shared mutable state. Now, because of that, because we don't like the properties of shared mutable state, we strongly encourage people to use value types when they can. But classes are still really important for a lot of code, such as their typical traditional use in a lot of UI programming. We don't want to make that code impossible or frustrating to write in Swift. That creates a problem for exclusivity. Here I've taken the previous example with a higher order function and rewritten it to use class properties. Now this code is going to make two references to the same mutable property of the same object. That's going to break value types all over again if I allow this. But the compiler can't really statically reject the code in the same way, just because the references might be the references ref1 and ref2 might be to the same object. We'd end up rejecting way too much code that's actually perfectly fine at runtime. There are a lot of ways that a language could extend a rule like exclusivity to class references. All the options on this slide have parallels in Rust, but they require dramatic changes to the basic programming model of class-based programming. People can't just write class-based code and simply read and write the properties anymore. They have to go through some extra syntactic overhead. For example, consider this very simple append to a class property. If I have to explicitly lock the object, one of the alternatives on that slide, in order to access its mutable properties, the code now has to look something like this. This would be a very unwelcome, heavyweight change for most class-based programming. And in practice, while the sort of reentrancy on class-based while reentrancy in class-based code can be a real semantic problem, it rarely leads to the specific aliasing issue that we're worried about protecting against in order to preserve memory safety in the language. So in Swift, we make a pragmatic choice to enforce exclusivity on class properties with implicit dynamic checks. When you read or write to a class property, the runtime checks whether there are any conflicting accesses to that exact property already in progress. That silently adds overhead to class-based programming, but allows that programming to continue written in the traditional way without undermining the basic memory safety of the language. That classes have this kind of extra overhead is something that we feel that advanced programmers can learn, and novice programmers don't really need to know about. When programmers do need to avoid that overhead, they do have several options. For one, if they can completely avoid shared mutable state, there's no need for dynamic checks, as we saw before. They can also use unique reference types, which are supported in the standard library. And we have a lot of room to explore other possibilities in the future. Let's look at another feature area, value ownership. When I say value ownership, I mean the set of rules for when and how values are copied and destroyed in the language. In this example, I have a string value in a local variable. I first add that value to an array and then print the value in the variable. Now, I said before that values belong to a single context at once. When I add this string to the array needs to own a value to store it. But then I'm still using the string later. That means I've kind of got the same value owned in multiple places. To make that work, I'm going to need to copy the string so that I have two independent values. And on this slide, I've made that copy explicit. Now, copying a value is not free. If the value is large, copying it might involve a lot of memory operations. If it contains object references, copying it might have to do reference counting or other memory management operations. These costs aren't likely to be millions of cycles, but they could add up to hundreds, and that is enough to matter for some very low-level performance-sensitive code. Now, if you don't want to copy like this, what else can you do in the language? Well, you can either consume the value or borrow it, and I'll explain those. Consuming a value means transferring it to a different context. This is a really efficient operation. You don't need to do most of the memory management. You just sort of need to move the representation of the value somewhere else, generally byte-wise. However, it has a big restriction. The value stops being available wherever it used to be. It's necessarily a strict transfer of the value. That means you can't always do this in the language. It's not a default option that's always available. Or you might have to rework the code to make it possible. In this specific example, I can consume the local variable to add it to the array, and then instead of reading the value from the local variable, I can just read it out of the array where I just put it. But that sort of convolution isn't always possible. Borrowing a value means using it temporarily without taking away the ownership of the original location. So this is our other option. Borrowing is a powerful way to avoid copies, but it also has a really big restriction. When we borrow a value, we temporarily have two contexts referring to the same value. That runs the risk of recreating all the aliasing problems we were just solving with exclusivity. So in order to safely borrow, we have to ensure that the variable that we're borrowing from is immutable, at least temporarily, during the scope of the borrow. This is a serious problem with something like shared mutable states, so class properties and so on, since the compiler can't enforce statically that you don't have multiple references to the same property. In order to borrow from something like a class property, we need to know that nothing else will try to mutate that property during the borrow. Suppose that we have something like a standard hierarchy of UI objects, which typically have parent pointers. And suppose that we try to borrow a node's current parent for some temporary purpose. How confident can we be that nothing during that borrow will reinterantly try to change this property during that borrow? As a result, borrows are also not really a simple thing that you can just do by default, because it's semantically affecting. So what should we do in the language by default? There's a clear conflict here between optimizing performance by eliminating copies or making them all explicit and maintaining the ease of use of the language, because we can't always borrow or consume, which are these efficient things that we know how to do. Making copies explicit would encourage programmers to find clever ways to optimize to avoid that. But that's not necessarily a good thing for the language. In a lot of code, a few extra value copies are unlikely to ever show up on a performance profile, and worrying about them isn't a good use of programmer time. In Swift, we don't think that's the right trade-off. Programmers shouldn't have to think about ownership unless they have a good reason to. So we implicitly pick a lot of things that have consequences for when and where copies are performed, like ownership conventions on parameters and so on. And we insert copies as necessary to preserve the naive source semantics of the program. However, since the core model that we use is based on this high-performance triad of copying, consuming, or borrowing, we can support a lot of features for explicit control in the language. Many of these features are already in Swift. Some of them are still being developed and imagined. And we think there's a lot of interesting research opportunities here for future work. Lastly, I'd like to talk about some of our more recent work on lifetime restricted values. This is an area that we're still wrestling with and would really open to ideas from the research community about it. Suppose that I want to write something like a tokenizer. I take in a string, figure out the extent of the next token, and then return it. What I've written here is a perfectly reasonable function signature if I don't really care much about the low-level performance of my tokenizer. If I do care about that performance, I've got a bit of a problem. String is going to be a normal managed value type in the language. So when I return a string, my caller is going to expect to receive an independently managed value. That token that I return needs to stay valid even if the caller throws away the original string. Depending on the implementation of string, this might mean doing extra reference counting or even an entirely separate allocation. That overhead can add up very quickly for something like a tokenizer that I might expect to call very rapidly in a loop. Now, the thing is, my tokenizer doesn't really care about the ownership of the string data, right? What I'd really like to do is just say, look, you give me a pointer to an array of characters, and I'm going to give you back a slice of that that corresponds to the next token, right? This is my low-level interface to a tokenizer. It's your problem as whoever is calling me to worry about how long that array and that slice are going to last. It's your problem. That would be a very efficient API with no added overhead for managing memory, just like you could write in something like C. Of course, in C, that would be completely unsafe. I allocate a buffer here. When I call next token. When I free the underlying buffer, token is now a ding-ding pointer. So if I use it, I've got to use after free. And you know, this is a bug that's occasionally been known to happen in C code. Like, it's caused some consequences for a few people. In Swift, we allow this to be made safe with what we call non-escapable types. So when we define a type like UTF-8 span, we can say that it is a non-escapable type. And this means that values of the type are always restricted to some scope. When we declare a function like nextToken, we can declare the dependency relationships between its parameters and results. So here we can declare that the return value has the same dependencies as the self parameter, since it points at the same memory. The compiler can then associate values with durations in the program. The compiler knows that the buffer is valid for this duration. The token value has a dependency on that scope, so all of its uses must fall within it. The print down here is outside of that, and so it's ill-formed. In Swift, we are still very actively developing our model and syntax for lifetime restricted types. Simple patterns like I just showed you are already in the language, but we're trying to come up with the right generalization for more abstract uses. This is a wide open research area, both for us and for Rust, which has and it continues to develop and iterate on a very similar feature. I want to very briefly drill in on one of those questions in particular. In Swift today, lifetime restrictions are associated with values. One thing that this means is that the dependencies of the value on a variable, the current value in a variable can change during its scope. Here, the array starts with no dependencies, then gains dependencies over the course of the function. This gives us a very permissive, flow-sensitive rule. We can use the array early in a way that might not be valid later in the function. In a world where restrictions are type-based instead, that doesn't immediately fall out. The lifetime restriction on the local variable array is part of its type, which is going to be the same throughout the function. The lifetimes of x and y then contribute to the inference of that lifetime restriction, but nonetheless it's expected to be the same, and so the use restrictions on the variable are the same throughout its scope. So this type-based restriction might seem more limiting, but we're still looking at making the switch. Putting lifetime restrictions into the type seems to give us a much better model overall, especially when it comes to generics. For example, we'd like the generic span type to be able to support lifetime restricted elements. Consider what that means for a type like span of UTF-8 span. Values of this type have lifetime restrictions associated with the outer span that correspond to how long that array lasts. But the values stored in that array also have their own lifetime restrictions. When the type-based restriction, we need to be able to express the fact that these restrictions are independent in a way. It's much easier to not conflate them if we can talk about the element restrictions as just part of the type of the element, rather than as part of weird dependencies on the overall span, like we have in our current model. And we think we found a way to not lose the flow-sensitive restrictions that we get from the value-based model by allowing the type of a variable to be refined over the course of its scope. But like I said, this is still very much an open problem for us, and we'd love to get more thoughts on it. OK, let's wrap up. I think I'm over time already. High-level programmers need different things from a programming language, but that doesn't mean you can't appeal to both at the same time. What you do is you build the foundations of the language with low-level programmers in mind, but hide those details by default so that your users don't always have to worry about them. Advanced programmers can be supported with more narrowly targeted features that reveal the underlying model. We encourage everybody to get involved. Swift has an open source design process, and we encourage thoughts and contributions from all comers. You don't have to be a Swift user at all in order to share your experiences with these ideas in other languages. And we really love to hear from you. Thank you very much.
OK, thank you, John. Please come up to ask questions. We'll turn the other mic on.
I'll ask one since I'm close. You're talking about this split between the needs of high-level and low-level programmers. How do you deal with that in the standard library? Do you have different views of the standard library for those different personas, or do you try to make a monolithic library that works for everyone?
Yeah, we have all of these features are available in the same standard library, but we encourage people both in our API design and our documentation, all of our training materials and so on, we encourage people to focus on the really standard and more general things. So with the array types, we have a copy on write array type. That's what we encourage people to use. It even has special syntactic sugar. All the other things are necessarily a little bit harder to find because they're less privileged in the language, right? And so that's the sort of approach that we take, right?
Hi, thanks for the talk. So I was wondering, in Rust, where we have those lifetimes and had them from the start, a lot of the standard library is designed around APIs that work well with lifetimes. That's one reason why the Rust standard library looks very different from the C++ standard library, right, even when it's basically the same type. Now, Swift is you're kind of now adding this to an existing language.
Right.
So do you imagine you're going to be able to kind of keep the existing APIs and make them work well in this context? Do you imagine you will have to add make the type system more complicated to account for that? Are you willing to change the standard library? Like, what's your take on that?
Yeah, I think for certain we're having some growing pains with some of the existing protocol designs. So like, especially around collections, the shape of those APIs is very much currently like doesn't really work well for non-copyable element types. So right now it's hard to write generic APIs over those things, and and that is something that we're basically just going to have to introduce a, like more refined set of protocols in order to deal with. But,
Yeah, so you've introduced this notion of escapable, which kind of binds the lifetime of an object to the inherent context, let's say. So like in Rust, we have like more fine-grained control over the lifetime. Let's say if your function has like 2 inputs, we can specify which lifetime, which of the inputs lifetime should be used for the output's lifetime.
yeah.
But like this escapable does, I don't think it has the same semantics, right? So what, like, is there any plans to like give us more fine control over like the lifetime?
Oh no, we can already actually express that sort of simple dependency already. Like you can, in a function signature, specify which parameter you're dependent on. Like that's basically a necessary in order, to do anything with non-escapable value. The non-escapable restriction is very coarse, but it just means that like the type in general has sort of restrictions. But the actual restrictions are part of the dependency signature of any particular function that you're calling. It's very similar in Rust, where Rust has, I don't remember but like there's a trait that tells you that a type is not scope restricted, and like, yeah. Nice.
Thank you.
Okay, let's say thank you once again, John. So if you could give it to Tristan. Apparently the other one is, yes. Yes, all right, so, while the microphone borrow and swap is going on, yes, I'll transition us to the second talk. So when I think about Tristan, I think about scale. So Tristan describes himself as passionate about binary analysis. Not sure a sentence I can fully comprehend, but, of course, that's something that requires immense scale to doing static analyses because, binaries are so large. And Tristan worked in binary analysis for about a decade during his PhD at University of Wisconsin and at Galois. But now he's taking this sort of to the next level at Amazon, where he's part of the automated reasoning group, and where he's looking to apply analyses on security properties for the services that power the internet, billions of requests per second. And I think hearing how the work we do can be scaled up in this important industrial context is what I'm most excited about in this talk. So Tristan, please take it away.
Thank you. Great timing. That was just enough to get all the display stuff worked out. So yeah, I'm going to be talking about some of the work we're doing in AWS in particular, but also used across the rest of Amazon too, if you're curious, on automating some evaluation of security properties and also like the sort of compliance assurance angle, if that kind of thing interests you. And the title is impenetrable, and I think it will make a little bit more sense as we go along. But I'll just tell you the takeaways now, and then you can tune out if you want. But we're using automated reasoning at scale to analyze all the services in AWS and build models of those systems so that we can do cross-service, cross-AWS analysis of security properties. And we're using those models to drive some of the other security tools that have been around and really powerful tools for a long time, but tools that required a lot more hands-on work from domain experts. And now we are using this automatic context inference to get to a place where we don't need to ask people questions. We can actually just answer security questions for them on their behalf. And then I'm going to go into some of the little details that never make it into papers, but that really matter when you're trying to analyze real code made by very clever engineers. There are some things I won't cover here. Scale, which is funny to say. We're talking about the scale of analyzing everything, but I'm not going to be talking about the scale of what do we do to scale up the individual like data flow analyses. That's really important, obviously, and one could imagine a whole separate other hour-long or so talk about that topic. And there was actually one earlier this week at SOAP by Michael Emmy. I think he's around if you have some questions on that. And I hope it will be recorded so you can actually see some of the algorithmic things we do to make this work at scale, the other kind of scale. But the background here is that the goal I have in this work is to be able to prove security properties continuously for everything in AWS and without having to ask any of our developers any questions about like what they're doing, what did they mean to do, what does their code currently do. These are all things that we can handle with automation now. So some example properties before we get into it, things like proving properties about data storage. We want to be able to prove and generate evidence for the fact that data is stored where we expect, when we expect it, and with the right levels of access. And ultimately, that's a graph reachability problem. Or at least it would be if you had a graph. Again, we don't want to have to ask anyone to build this graph for us, so we're going to build it. There's also a whole family of properties, and this is not exhaustive, this is just indicative, but things like proving that services are configured with least privilege access. There's a very powerful permissions mechanism for controlling what different services have access to and at what times. And we want to always make sure and to be able to provide evidence that each one of those services has only the permissions it needs and no more. So if you have a service that has been given a set of permissions, that's like an IAM role, you can also imagine that there is a set of permissions that it actually uses. And in this, I've labeled those as P1 and P2. The problem of proving these privileges is proving that P1 equals P2. And I'll have some examples later, but what we really want to do here is get P1 automatically and also calculate what P2 is without asking anyone what P2 is. And then once I have that, I have access to this other very powerful tool. All AWS customers do, IAM Access Analyzer, that reduces questions about permissions down to SMT, and that lets us automatically answer these questions if we can get P2. So we need models of our systems to be able to answer these questions, to get this context so that we can actually answer these with automation. And that gives us sort of the operational context. So the model will tell us where things are executing, what they have access to, how they do their jobs. And if you're thinking about models, often you might see something like this. People will draw a picture, and a picture is a good way to view a model, but it's rarely that easy. But this is an example of a picture that I would draw for the system that is sort of like the notional system for this talk. It doesn't do anything in particular that's interesting, but it gets across this idea that what I'm analyzing is an AWS account, which is full of resources and full of compute. The compute are the orange things, that is where your code runs and does things with the data in the account. You can see that the requests enter this system because it's a web service. Requests enter on the left-hand side. They are routed to a piece of compute that logs data. It sends data to an object store. It sends data to a database. All the usual kinds of things you would expect. This is a nice picture. And if you built this system, you could draw this picture. But if someone gives you an arbitrary system or gives you thousands of arbitrary systems that you don't know anything in particular about, it looks a little bit more like this. It is a collection of things, and you have to figure out or recover what they're doing. So that's what this talk is about, recovering a model from that. So what we're going to do is use automated reasoning to do this. There are going to be 3 steps, 2.5 steps. I don't know how you want to count it. We're going to start off by analyzing the infrastructure in that account, just having it describe itself. Then we're going to analyze the code. That should be unsurprising given the venue. And then we're going to combine those things into one merged system model. One nice thing about working with in this domain of web services and like an AWS account full of resources, it's self-describing. You can actually go and probe the account and ask it to list off all the resources in the account. And moreover, you can actually get each of those resources to tell you how it's configured. And that's really useful all by itself. So if you just ask this account, hey, what's going on? What's in there? How is it configured? You can reconstruct part of the model on the right-hand side. And you can get some reasonable details here, like the purple thing at the top on the top right. That's a database that's plumbing or piping some data to what's called a Kinesis fire hose. That lets you transform the data and then make copies of that data into other data stores. You can see that there's already some information about requests coming into the system through that API gateway being routed to a Lambda for processing. You can see that Lambda logs some data there. So that's part of the model we wanted. And that's pretty cheap. This is very easy. You don't have to think very hard to do this. But you'll notice that there are some gaps compared to the picture that was there before. And of course, those gaps are the orange parts. That's where the code is running. This is really important to understand the behavior of a system, though. You need to know what the code is doing because the code is receiving requests, picking data apart, combining it in new ways, transforming data, putting that data into new places, interacting with other systems. That's where the really interesting parts of your system happen. And to do that, you actually have to analyze the code. And we don't want to run this code to figure out what it's doing. That would be just logistically really hard. But we can use static analysis. So surprising no one, no one here at least, this is abstract interpretation. We're going to use static taint analysis. And what I want to build here is a data flow map. And to do that, I'm just going to label every input, every field of every input to all of the services I have access to. And then I'm going to use static taint analysis to say, where does that data go? And that lets me collect this set of connections that are induced by the code that's actually running on the systems. And that gets me a nice little bipartite graph that is the map from inputs to outputs of what the code is doing with its data. And then that lets me complete the picture. So I had the previous picture from just analyzing the infrastructure. Now I can add in the edges that arise from the actions of the code itself. And because it's abstract interpretation, I get some nice bounds on execution time. I can run it on everything. I don't have to worry about how do I actually take an unknown piece of code and run it as it would run in production. I can just evaluate what it's going to do over all possible paths with a sound over approximation. Now, this is where you would probably want to look into the other talk for some of the details. There's a lot going on here where, this is a whole program analysis. And when you want to do a whole program analysis over all of your dependencies, you can easily run into the millions of lines of code. So there's some really fun scaling challenges. To get the precision we want, we end up needing at least object sensitivity, and we end up finding interesting patterns that need to be handled in exciting ways because even just going with object sensitivity by itself isn't quite enough. We have to support multiple programming languages because inside of Amazon, pretty much every programming language has its place. We have to do some interesting work to model things like reflection. So a lot goes into this part of the stack analysis, but that's not where I want to focus this talk. I just want to say now that we have all that information, we can go back and build that model. This is roughly the model you would get if you asked an expert to go build or to draw the model of how they understand their system. I have actually done some work here to collapse all those edges. There's a lot more detail here because we're tracking things at the level of individual fields. But if you draw all of that, it turns out that the diagrams get pretty useless because there are too many edges. So we go with the simple one when we're drawing it for exposition purposes. But under the hood, this is not a picture. This is actually a data structure that you can then start automating security questions on. So like I talked about before, that includes our graph reachability problems over the full AWS stack. And then also going back to the least privilege question, I can fill in some of the details I glossed over. So again, least privilege in this context is us wanting to provide evidence that when a service has a set of permissions granted to it, it uses all of those permissions. It's not over-provisioned in terms of permissions. So I can get the IAM policy that grants those permissions on the left. Those are the ones that has actually been granted. And I can construct the policy on the right that describes what it actually does. And this is what it can do on all possible paths of execution because we have a sound over approximation thanks to our abstract interpretation. And then I can use that to feed this other tool, IAM Access Analyzer, which turns these two policies into an SMT query that proves that they are, in fact, the same policy. And in this example, they are not. You can see that there is an extra permission that it has access to that it doesn't actually use, and that would be something that you would want to change by modifying the role assigned to it so that it is actually running with least privilege. And because this is all automated, we can do this for everything, which is great. And we've done it without asking anyone any questions, which is even better. But now the more fun part of the talk, for me, is that the devil is in the details. All of those things kind of follow from the sort of standard algorithms that you would imagine in the world of data flow analysis, abstract interpretation, taint analysis. But then there are the things that never make it into the papers or into the textbooks, at least not that I have seen. Just the engineering you need to do around the edges to really understand these systems. And I'm going to focus on two things. This is not exhaustive, but configuration and serialization. So I find this exciting. This is where we end up spending a surprising amount of time because we need to handle this for all of the interesting cases that we run into. So I've written on the slide that this is the complexity of real code. This is not real code. This is completely made up code, but it is indicative of what you would see in a typical web service. It is running in some sort of web service. It takes a request object, and you can see in the orange, it uses some information from that request to go fetch data from a database in the call to get item, and then it constructs a new piece of data, and it puts that into an object store in the call to put object. And that's great. Just by looking at this with a normal static analysis, we would be able to see that it is interacting and pulling data from the database and putting object into the object store. But that's not what we really want to know. What we really want to know is which object store, because if you have 50 different object stores, building a data flow map that just tells you that the data goes into an object store, that's not very useful. You need to know which one. And that's the data that I've highlighted in green, which is a very interesting green on this screen, but it's the name of the database table and the name of the bucket that's the data is being stored into. Those are what we really need. And you might say, well, just use constant propagation. And you're right. You're partly right. But the challenge is that it's not actually in the code at all. These things are set early in the execution of the program, often when it started, but the values aren't in the program. They come from configuration files. They come from the environment variables. Sometimes those environment variables are set by shell scripts. So you have to understand everything in the environment to be able to fill in these values. And that's actually what we do. We have code that runs before the analysis that analyzes the execution environment and introduces the constants that are introduced into the system at runtime. It introduces those statically at static analysis time by interpreting the environment. So that's like pulling configuration files, parsing configuration files, pulling environment variables that are configured for lambdas, doing things like analyzing shell scripts to figure out what are environment variables actually set to, doing the analysis in the context of different regions because you might have different values in different regions. So you might have to analyze the one running on the East Coast versus the West Coast versus Europe with the different values to really understand in each of those contexts what is being done. But once we have that data, we can introduce those constants and then just use constant propagation like you would expect to get the results we want at all of the data syncs. So again, at this get item call and the put object call, now we have that context we need, the name of the bucket, the name of the table, and we can build the data flow map that I showed before. There's another really fun example, and I didn't appreciate this one as much when I started this project, but I definitely appreciate it now. This is just a slightly modified version of that code snippet from before. I've got a request coming in, I pull some data out of that request, and I assemble a new piece of data, the thing in blue. It doesn't really matter what it is here, but it's basically a 3-tuple of some of the input data, some fresh data that's coming from this timestamp. And then what am I doing? I'm putting it through something that happens billions of times a day, maybe trillions, all up across the system, but I'm serializing it as a JSON value, and I'm storing it in an S3 bucket. Well, that seems pretty straightforward. And if you just think about what taint analysis would do here, just like a normal taint analysis, you would say, well, that string that is being stored in S3 has 3 different taints in it, or maybe 2 if you're just tracking the account ID and user data. And that's true, but it's not the most useful, because now the other part of this is that someone else, some other service, is going to pull this data out of the S3 bucket and do something with it. And I really want to know which of those pieces of data are they using and where did it come from. And if I've smashed them all together into just a string, I lose that information. I think you might just say that they're using all of that data, and that's too imprecise. That means you'll start, you might start seeing that user data appear in places that it's not actually used, because maybe the data consumer is only pulling out 1 of the fields or 2 of the fields, but not the user data. And you don't want to have any sort of false report that, or some imprecise report that the user data is somewhere you don't want it. So where we end up here is that we actually have a lot of extra work inside of the taint analysis to be able to retain this structure. So this is really special handling for different kinds of serialization libraries and deserialization libraries, because we need to be able to do this symmetrically on the other side of the system when we build the model. So it is in some sense unsurprising, but it is also almost as much work as the rest of the analysis by itself in some ways. So we end up having models of the different serialization libraries used across the whole system so that we can do this level of precise reasoning. I could probably go on all day, but I'll save some time for questions. The most important part of this slide is that we are hiring, and if you're curious, you could scan that QR code. We also have a booth or a table out in the lobby. But from this talk, I just want to again, remind you that what we're doing is using automated reasoning to build models of all of the systems in AWS so that we can do this security analysis continuously. And while you're doing this, it is really interesting to see what you need to do that doesn't make it into the papers. And you might think that it's not that interesting, but it's really that last mile of work is critical to getting the types of results you need to get precise answers across the whole fleet.
Microphone, I think both work.
Do you ever show these models to developers? Because I expect they'll, one, be able to spot issues with them, but also might find them useful as like dynamically generated documentation.
Yeah, absolutely. Lots of people want to see the models, because often, when you design a system, you build a model like this and you say, yeah, this is what we're going to build, and then you go build the system, and then no one ever updates that. So yeah, people are absolutely excited to see this type of model and check their understanding, use as onboarding material for new hires, because if it is pretty frustrating to join and then get shown some documentation that is very out of date and not understand, like, oh yes, this is what it looks like now. Being able to have that handy is great.
So you don't show it to them yet, but you're hoping to.
Oh, we've shown some. It's not something that we give to everyone and say, here is your system, but when people ask, yeah, we absolutely share them.
Thanks, yeah, that was interesting. So you talked about mainly how to find out what the ground truth, what the code is doing. How do you figure out what properties you want to check about the code?
So what properties we want to check? Well, there are, from the security perspective, there are all sorts of properties that we always have in mind that are universally true for all of the systems. So those are kind of like, I think of them as free properties. They have to be true. And then there's some other work going on where I'm in the process of building out more tailored specifications to each of the other services. So those give rise to other properties you would want to check that don't necessarily apply to every system, but apply to the ones where you know what they're supposed to be doing.
Right. Okay. So you're not at least in this project you're not mining the specifications. You have general specifications, or you're getting them from a separate source basically.
Yeah. So not mining specifications right now, not as such, but one really good source of those specifications that I would like to explore more is just straight up the public documentation. Each service makes promises about what it does. That gives you derived specifications that get to filter down through the rest of the system.
Right. Thanks.
Hi, good talk. Just curious, like for more dynamic languages or languages with more metaprogramming, it seems kind of hard to catch statically all these different relationships. And I'm curious if you do any sort of dynamic verification, actually instrumenting to see like if any of you haven't caught any of the paths.
We haven't done any dynamic analysis, so we're confident that we can compute an over-approximation, but to your point, the over-approximation might be unpleasantly large for some kinds of languages, and actually my preference is, if something is too dynamic and too wild, I would rather say I don't know than give a very over-approximate answer, but there are some really interesting avenues to do some mixed dynamic refinement. So there is a thing, I think it's a service, a feature, I don't know. It's called X-ray, and it actually gives you a trace of calls through, like if you issue a call, it'll tell you like what other calls are being made on your behalf to service it. So that's one place where you could actually do some validation against a ground truth of observations, and that's sort of an under approximation that might help. It might help.
Thank you.
Okay, let's do another round of applause. Okay, that concludes our industry session. I want to call out that both John and Tristan will be here. You can find the booths right outside in the lobby. I'm sure many of you have additional further questions you'd like to ask. And now let's please go to the lobby, and I think we have student research competition finalists as well.